So kind of a quick and brief look back at where we've been and where we are. We started this course with a lot of descriptive statistics. The problem with our computer age is it's really easy to generate tons of numbers, but you can't look at a bunch of numbers to make sense out of them. You need to summarize them somehow. So you need to display them, you need to summarize them. We found means, standard deviations, range, etc. So that was all our descriptive statistics, and then displaying that kind of stuff with histograms, frequency histograms, relative frequency histograms, etc. was all part of chapters 2 and 3. Then we moved into probability and discussed some few things about probability. That probabilities are between 0 and 1. We discussed different types of events. There was mutually exclusive events. If one happened, the other one couldn't. There was independent events, so that the probability of one doesn't depend on the probability of the other. And eventually that led into a discussion of the normal distribution, which is kind of like the foundation for a lot of the rest of this course. Normal distribution had a nice bell-shaped curve with an area of 1. It was symmetric. We have tables with their probabilities, etc. We looked up areas. Then we also dealt with the central limit theorem, which said that x bar has a normal distribution no matter what population you're sampling it from. As long as you have a sample size of at least 30, then it's going to have the same mean as the population you're sampling, but then its standard deviation is going to be divided by the square root of n, so that the larger and larger you sample, the less variation in this distribution, and chances are x bar sub n is going to be a good estimate of your population mean, regardless of your sample. Now, you know that if you take more and more samples, you're going to get different results. They're all trying to estimate the same thing, though. In the case of a mean, your sample mean, you hope, is a good estimate of the population mean, but you know that it's not necessarily going to be exact. You know it might be off by a little bit. So you surround that mean by a confidence interval. So x bar is your best guess, your point estimate for the population mean. But realizing that you might be off by a little bit, we surrounded it by x bar minus e and x bar plus e. Or in the case of a population proportion, we did the same thing. We knew that these estimates might be off. So we said, you know what, let's surround it by a confidence interval, and we can state pretty confidently that the true parameter, whatever it is within these intervals. So we're starting to branch out. We started with descriptive statistics. Now we're moving into inferential statistics. We want to go beyond the data and make generalized claims. And this is what's different about a statistics class as opposed to a math class. In a math class, you prove things. And raise your hand if you had to take a geometry class. Should be everybody. I don't think you can graduate high school. Raise your hand if you liked geometry. All right. And so for the benefit of my viewers, I'm not raising my hand. I did not like geometry. My kid's going through geometry right now, and I really get nightmares revisiting that subject. It wasn't my favorite. But anyways, we're going to go beyond our data and try and make inferences. Instead of proving things deductively like you prove in math, you're going to make inferences. Now, these inferences are going to extend to population parameters. And that's what we're going to do, is we're going to start testing claims about a population parameter. What would be some examples of parameters? Feel free to use Greek letters. Mu, good. What else? Sigma. And the last one was P, our population proportion. So these are population parameters, and we're going to test claims about these things. So when you start working with your hypothesis should have one of these parameters as part of it. Now this is how it's going to work. We're going to assume that something is true, and then try and decide whether or not we think it's true or not. And it's going to be based on this idea. If under a given assumption, and this is your rare event rule, the probability of a particular observed event is extremely small, then one of two things happened. Either you observed something that was rather unusual, or your assumption was wrong. And we're going to conclude is that our assumption probably wasn't correct. And that's going to allow us to go beyond just a deductive process like you do in geometry and prove things. So we're going to start testing claims about hypotheses. And in this section, we're going to introduce you to a lot of vocabulary about that. We're going to start out with something that we're going to assume is true. We're going to decide on a level of significance. And then this stuff is kind of old school. So, old school. Where you find the critical values and compute a test statistic. You can do it that way. And that's kind of outlined here. Critical values are going to be based on a particular distribution. And depending on if you have a left tail test, a two tail test, or a right tail test, you're going to put your level of significance in one tail or another. But we're going to take a little bit of a different approach in this class, especially because we have a lot of technology available to us. And I think you're really going to like this because it's going to make our lives so much easier. We're going to input the data, whether or not it's raw data or summary statistics, doesn't matter. And instead of computing the test statistic, well, we'll let our software compute the test statistic. We're going to find something called the p-value. So find the p-value. And if you understand the p-value, you can actually understand a lot of statistics. Stuff that you might not really fully comprehend. You can decide whether or not you should reject or accept the null hypothesis simply based on knowing this p-value. And understanding this is going to get us a long ways. So, first things first, though, we have to set up some hypothesis to test. And let's talk about that a little bit. We're going to set up a null and alternative hypothesis. So setting up a hypothesis. Now we're going to have two hypotheses, H sub 0 and H sub A. Also might be referred to me as ho and ha. All right, ha ha ha. But this is your null hypothesis. This is what's going to be assumed true. And then, of course, this is your alternative hypothesis. This is what's true if your null hypothesis is false. Typically, that's what you're trying to prove. You put what you're trying to prove in the alternative hypothesis. Now, a few things about the null and alternative hypothesis. H sub O and H sub A are mutually exclusive and exhaustive. And what that means is that if H sub O is heads, then H sub A is tails. You're one or the other, and that's it. There's no more choices. You either rolled a 7 or you didn't. You made your point or you didn't. So it's one or the other, And that's it. That's all the choices that there are in the universe. H sub O has to have the possibility of equality. Has to have the possibility of equality. I.e., it's going to have a less than or equal to, or greater than or equal to sign in it. It has to have that possibility of equality. H sub A won't have that. H sub A is going to have less than or greater than sign or not equal to sign. Less than, not equal to, or greater than sign, depending on the problem. H sub A is what you want to prove. And last but not least, H sub 0, H of O, is what's assumed true. That's where you're going to start out, by assuming that that's true. Let's start out with problem number 6. When parents use the XORT method of gender selection, the proportion of baby girls is greater than 0.5. So let's see if we can't set up a null and alternative hypothesis. First of all, what parameter is being tested? Should I list a mu, a sigma, or a p? P. Now, the part that should catch your attention in setting these things up is this part right here. The proportion of baby girls is greater than 0.5. That's part of the claim here. So if you wanted to show that, that's going to be part that's in your alternative hypothesis. So for problem number 6, P is greater than 0.5. That has to be in your alternative hypothesis. This is what's called the original claim. The importance of that we'll come to in a little while. If that's your alternative hypothesis, what has to be the null hypothesis? What's kind of the opposite of that? Yeah. P is less than or equal to 0.5. So you're one or the other, right? There's no middle ground. Now, just a quick FYI, the author would just list P equals 0.5. I like this P is less than or equal to 0.5 because it makes it look a little bit more complete, because you're one or the other. You're not both. You can't be both. There's no overlap between these things. And between these two statements, we've covered everything. So I'm going to stick with the habit of writing less than or equal to 0.5. If you wrote equal to 0.5, that's completely fine. Are you okay with how we set up the null and alternative hypothesis? When I grade exams, one of the things I'll be looking for is that you have a population parameter here, not a test statistic. Your sample statistic here is going to be your p hat. But I want a sample statistic there. Let's read the rest of it. So it says the actual results show that among 945 babies born to couples using XSort, the method of gender selection, 879 were girls. Wow. What do you think? Do you think, not doing any formal tests, but kind of looking at things informally, do you think we would reject the null hypothesis in favor of this one? Yeah. And results like that are astronomically low in terms of their probability. So yeah, I would say that that's strong evidence to support this claim, that you have a much better than 50% chance of conceiving a girl. All right, we're going to do one more like that, problem number 8. Before I move on, is there some more here that I could add that might help you out a little bit? Okay, let's move on to problem number 8 then. Claim the standard deviation of pulse rates of adult women is at least 50. So let's take a look at that part of our work. Standard deviation of pulse rates of adult women is at least 50. First of all, what parameter are we testing? Sigma. Good. So we're testing sigma. Sigma is at least 50. What symbol should I use here for at least? Greater than or equal to 50. Now, Carlene, if I'm using a greater than or equal to, is this part of my null or alternative hypothesis? Good. Part of the null, because the null includes the possibility of equality. Charlotte, how about the alternative hypothesis? If this is greater than or equal to 50, what's the alternative hypothesis? Yeah, less than 50. Thank you. So notice you're one or the other. That's it. There's nothing else that we could be here, right? You're either at least 50 or you're less than 50. All right, the rest of it, we'd have to pull out data set 1. We're not going to take the time to do that. The goal here is to spend a little time setting up your null and alternative hypothesis. Believe me, as we go through the rest of the course, we will get plenty of practice in that. Okay. Now, once you have your hypothesis set up, then we're going to be making some decisions. We're going to do some tests and make some decisions. Now, we're not going to know what the truth of the matter is, but we're going to make a decision. So this should be on your handout. Let me go back to, yeah, this one will work. So we're not going to know necessarily what the truth of the matter is. There is truth, but you might not always be able to figure that out. Nonetheless, we have to make a decision as to what we think is true. Is H not true or is H not false? And that leads to kind of a little table of things. Now, not knowing what's here, we'll decide what we think about H naught. If H naught is in fact true, and that's our conclusion, yay, it's a correct conclusion. If it's false, and we conclude that it's false, that's another correct conclusion. Yay. So it's nice if you got it right. But there's also some things that can go wrong. And I've got the definitions here to the side. You can make a type 1 error. That is, H naught is true, but you decide to reject it anyways. Your data leads you to this conclusion that, you know what, H naught is false, but in actuality it was true. So you made what's called a type 1 error. Now the probability of a type 1 error is this guy. right here. Does that look familiar? Alpha. That's the same alpha we've been using all along for like our confidence intervals. So that alpha is not a mistake there. A type 2 error is when you conclude that H0 won't be rejected, you conclude it's true, but in fact you really should have rejected it. So it's another type of error that you can make. So there's two types of errors. You can make a type 1 error or a type 2 error. Now, typically, this is the one that you can control the most and the best. And this is the only one that we're going to see in this course, really, is the type 1 error. So let's work on that. Let's flip it over to the back side of our handout. In the United States, if you have to go before a jury, you're accused of committing a crime, then the null hypothesis here is that you're innocent. What would be the alternative hypothesis in this case? Guilty. So let's try and understand type 1 and type 2 errors in this situation. So this is the truth of the matter. The truth of the matter is that you're innocent or you're guilty. We don't know which. The jury decides. So here's the jury's decision. If they decide that you're innocent, and in fact you are innocent, well, that's good news, right? That's a correct decision. So that's one thing that can happen. Another thing that could happen that's a correct decision would be down here. If you're guilty and they find you guilty. So that's another correct decision. But a type 1 error is down here. Your null hypothesis is true, but you reject that. Now, a lot of times on an exam, I'll ask you for to describe a type 1 error, and I don't want the definition. Let me repeat that. I don't want the definition. I know what the definition is. I want you to describe it in terms of the problem. In this case, a type 1 error would be convicting, because that's the jury's decision, an innocent person. Another possibility is this one, a type 2 error. In words that relate to the problem, what would be a type 2 error in this case? Yeah, a guilty person being set free or being found innocent. So, guilty person being found innocent. Now, it seems to me that in our country, of the two errors that you can make, the worst of these is this one, your type 1 error. We don't want to see an innocent person convicted, and it seems to me that our legal system is set up to try and make this one less likely than this one. So, now, like I said, you can, to a certain extent, control the probability of these errors, and you can make decisions based on the consequences of, well, what does it mean if you make this kind of an error? So if you want this error to be really, really small, okay, you can do that. But sometimes it's going to make the probability that this error occurs bigger. They're not always mutually exclusive, but increasing one probably decreases the other. All right, so you'll adjust these depending on the severity or the consequences of your decisions. Of well, gee, what happens if you make a type 1 error? If you're building mine detectors for the Army, you want to make sure that they're working. Consequences of saying that one works when it doesn't are pretty severe. You'd want to make this really, really small. Let's try this again with global warming. Now, as I said earlier, the hypothesis that you want to prove typically goes in the alternative hypothesis. If you want to show that global warming is real, you start out by saying, let's assume it's not, and investigate that premise. If it looks unlikely that you could see 10 or 11 different indicators of global warming all pointing in the direction of global warming, then maybe you think that, oh, you know what? Maybe that's unlikely enough to the point that we can assume that this assumption is wrong. Okay, so I've labeled type 1 and type 2 errors. Take a moment and try and put into words what a type 1 and what a type 2 error is in these situations. Need a few more seconds? I got this. Keegan, what do you think a type 1 error would be?
Facts say that it's real. Not really sure.
Some help? Maybe? Global warming is real, but global warming is real. So that's what's true, but here's your conclusion. But research concludes that it's not. Research to global warming is not real. Thank you. Not real. But research concludes that it is real. Okay. How about a type 2 error? What's happening there? So in reality, at least the way we set it up, in reality, global warming is real. Global warming is real. But what? Yeah, but the research concludes that it's not real. But the research concludes it's not real. Now I'm curious yes? So we're assuming that global warming is not real. So that's your null hypothesis. And if you reject that, then you're rejecting a true null hypothesis that global warming is not real, and you rejected that. So that would be a type 1 error. On the other hand, if global warming is real and you failed to reject the hypothesis that it's not real, you didn't reject that, then that's a type 2 error. So you have a false null hypothesis that you failed to reject. So that would be a type 2 error. Okay? It takes a while to sink these things in. Now, I do have a question for you. Which one of these errors do you think would be more severe? Which one were you like, you know, if I had to make one of these errors, I really wouldn't want to make that one. Yeah, I think type 2 would be the worst of the errors to make. Because if we're going to turn planet Earth into a raisin, we probably better know that and do something about it first. So, okay. So a little bit of work on type 1 and type 2 errors. Just got too much stuff up here. Now, the one thing that I'm looking forward to a lot in this course is, for me anyways, a different approach to deciding whether or not a null and an alternative hypothesis is going to be true or false. So we're going to do the p-value approach to hypothesis testing. That approach is on page 390 in your book. But let me try and explain what the p-value is. So the p-value is a probability. It's a probability that if the null hypothesis is true, you could have gotten something like you did in your data that's at least that extreme against the null hypothesis. So probability that the null hypothesis is true given the observations in the data. Now, if that probability is small, then we're going to apply the rare event rule. If that probability is small, we're going to start tending to think that, you know what, I don't think the null hypothesis is true. And I'm not sure where I picked it up, but this is kind of a nice little mantra that you can keep in mind. If the p-value is low, H0 must go. So low p-values mean, you know what, reject the null hypothesis. And this is going to be kind of an end round around a lot of calculations and stuff that we're going to have to do or not have to do, really. So it's going to be a nice thing for us. And these p-values aren't necessarily easy to come by, especially for you guys, if you're doing it old school. In fact, I used to have a whole handout on finding p-values. You can still find this in the book, but you know what? Your graphing calculator, any of your stat packages, StatDisk can give you and will give you your p-value. So that's good news. What we're going to have to worry about is, deciding or finding that p-value and making the correct decision. So let's test a couple claims. Problem number 26. So the nice thing is that I can give you problems that won't necessarily require you to put things into statistics. If I just give you the p-value, say, okay, here's the p-value that you would get, you make your decisions. All right, that's the wrong section. My bad. Yep. Okay. So our original claim is that fewer than 20% of M&M candies are green. Hypothesis results in a p-value of 0.0721. So let's take a few things. Let's see. So the percentage of M&Ms, green M&Ms, is less than 20%. So I'll do this. P sub G is less than 0.20. Personally, I like to put this little notations here instead of just put P is less than 0.20, P sub G. And the reason for that is because eventually we're going to be working with two populations, and you're going to need to keep things straight. Are you working with one group or another, etc.? So this is our original claim. And it's important to keep track of that because we're going to spend some time on how to phrase your conclusion. Right now, though, is this going to be part of our null or alternative hypothesis? Alternative. Liam, what should I put in my null hypothesis? No, still talking about green ones. Sabrina? Yeah. Greater than or equal to 20%. Thank you. So that's one or the other. You're either more than 20% or at most 20%. But there's no overlap, right? There's no way you can be in both camps at the same time. There's nothing that satisfies both of those. All right. We're going to test all the claims in these next few problems at the 5% level. So alpha is 0.05. And we came up with a p-value in this one of 0.0721. So what would you decide about the null hypothesis? Would you reject it or would you fail to reject? Let's go back here. If the p-value is low, H naught must go. Well, is this less than my alpha? No. So what this is saying is that, yeah, what we observed is not very likely. It'll happen about 7% of the time, but it doesn't quite cross the threshold of it's that unlikely that you're going to get this kind of result to the point that we want to reject this. So we would fail to reject H naught. Now, let me make a couple remarks about this. First of all, notice we didn't say we proved this. You don't want to say you proved H naught because you start out by assuming H naught. When a jury comes back and says not guilty, did they really prove he was innocent or did they just fail to convict? You know, it's somewhere in between, but you're not going to prove that that's true. Similarly, we're not going to prove that this is true, although we can feel pretty confident. We feel that this is likely to be the case, but we're not proving anything. You're not proving anything in a stat course. Statistics is the art of never having to say you're sure, which doesn't always work good in relationships. I'm pretty sure I was faithful, honey. All right. Not sure that would go over too well. All right. One other thing. 5% is just really came from a kind of a flippant comment. There was a statistician in the early 20th century by the name of R.A. Fisher. And he said one time, well, you know, you should establish this should be true to within, you know, a 1 in 20 chance. So that level, 1 in 20, 5%, that kind of stuck. So when you're doing your test, quite often you'll see alpha is 0.05. Another very common level is 0.01. Those are the two common ones. But the nice thing about giving somebody a p-value is they can decide how carefully they want to test things. You know, do you have enough evidence to reject the 5% level but not at the 1% level? Yeah. Again, it's going to depend on what are the consequences of a type 1 or type 2 error. Okay, let's try another one. Are we okay with our decision here? The p-value was greater than alpha, so fail to reject. That's it. Yes, sir. Yes. Yeah. Alpha's not something you're going to have to decide. When I grade you on these things, I'm going to be giving you alpha. And so there's not going to be any points distributed for alpha. There's going to be some points for stating a null and alternative hypothesis. You'll be given this. Your critical values and your test statistic, all that's going to be wrapped up in a package like StatDisk or Minitab or SAS or SPSS. And then I'm going to grade you on, did you make the correct decision? In this one here, the correct decision was to fail to reject. And then last, and certainly one of the most important parts, is state your conclusion carefully in words. And the idea here is you don't want to tell whoever you're getting the results to, oh, I rejected the null hypothesis. They're going to look at you like, well, what does that mean? What you need to tell them is, oh, well, you know, our research concluded that, our research didn't support the claim that there's less than 20% green M&Ms. So you have to state it in words that would make sense to a layperson. Anything else before we do problem number 28? Okay. Let's move on then to problem number 28. Original claim, women have heights with a standard deviation equal to 5 centimeters. The hypothesis test results in a p-value of 0.0055. So let's start by setting up our null and alternative hypothesis. The original claim is that the standard deviation of heights is equal to 5 centimeters. What parameter am I testing there? Sigma. So the original claim is that sigma is equal to 5 centimeters. Nikolai, is that going to be part of my null or alternative hypothesis? Yeah, it's going to be the null. Jacob, how about the alternative hypothesis? What has to be in the alternative hypothesis then? Yeah, it's just not equal. We're not saying what it is. We are saying it's just not 5 centimeters. Now we're going to make this test at the 0.05 level as before. And in this case, they give us the p-value is 0.055. What I want you to do is decide what you think and then compare notes with a neighbor. See if you're on the same page. Do you reject or do you accept? But take a few seconds and decide what you think on that one. feel free to converse. It's okay. You have my blessing on that one. Okay, so is P low enough to reject? Yeah, absolutely. So reject H naught be our decision. There's enough evidence to support the claim that the standard deviation is different than 5 centimeters. Cool. Would you like one more like this, or are we okay with the p-value and how it's used? We're definitely getting a lot more practice on it. So the last little piece here is the actual wording of your conclusion. Now this is kind of a sticky point. So got a nice handout here that tells us exactly how we're going to word our conclusion. And I strongly suggest that you pretty much stick to the script. I mean, I'll take some variations, but this should not. Do you need one more there? All right, I'll get you one when we're all set here. So the wording and conclusion. It starts with your original claim. So if you notice in several of these examples, I noted carefully what the original claim was. Does your original claim contain the possibility of equality? Yes or no? And if it does, what was your decision? And based on your decision, and based on the original claim, then this is how you can word your conclusion. I strongly suggest you stick to this script. Let's look back at the 2 problems we just finished. So the first one dealt with the proportion of green M&Ms. And our original claim was this one right here. That was our original claim, that the proportion of green M&Ms is less than 0.20. Okay. Well, what happened with that claim? We failed to reject it. Let's see how that compares here. Does your original claim contain the condition of equality? What do you think? That's a less than. There's no possibility of equality here, so does your original claim contain the condition of equality? No. What did you decide? Reject or fail to reject? failed to reject. So this is how you'd word it. There is not sufficient sample evidence to support the claim that, and now you put your original claim in words. The original claim was that the proportion of green M&Ms is less than 20%. So if you just follow this little guide, you should be okay. So problem 26, our conclusion is there is not sufficient evidence, and I think the author puts in the word sample evidence to support the claim that the proportion of green M&Ms is less than 20%. So, like I said, most of this is kind of plug and chug. Up to about here, I mean, this is something that you can write kind of almost in general. And then the rest of it is just stating the original claim in words. Let's do this for one last one, and then we'll take a break. So, it's problem number 28. And back in problem number 28, the original claim was this one, that the standard deviation of the heights of women was 5 centimeters. Eventually, we rejected that claim. So see if you can't follow your way down the path on this little handout to figure out the correct wording. You can help each other out too. That's a good idea. If you're not sure, I'll kind of walk around a little bit. If you want to stop me, that's great. But help each other out.
It's still inequality. So it does the original
So
claim.
the original claim was that the standard deviation of women, the heights of women,
The
is
equal
5.
sign is
So
inequality.
this is your original claim right here, and it includes the possibility of equality because it's equal.
HO has
So,
to have the possibility
yes.
of equality.
And then
equals
here, did we reject?
20
Yeah,
is
so
Reject O because the evidence suggests women do not have the heights.
right, but still, this is still inequality. Even though, and then you go from this question, do you reject? Yes, we did reject it, so you
You're saying it should be here.
put this one.
it was rejected. So, getting this one pretty good. So our original claim, and it's something that you might want to note for yourself as you're going through these problems. Your original claim contains a possibility of equality. So all right, that's good. That branches us here. Did we reject it? Yeah, we did reject. So there is sufficient evidence to warrant rejection of the claim that the standard deviation of heights of women is equal to 5 centimeters. So, are you okay with 28 here? All right, I think this is a good place for a break. So for homework, try 1 through 11, 25, 27, 31, and 32. I think a quick note. One of the things that I kind of avoided a little bit was the actual work of finding the p-value. And the reason for that is there's technology that'll find the p-value for us. So the important thing is you understand where and how to use it. If this is less than alpha, you reject the null hypothesis. If it's more than alpha, you fail to reject. Make sure you don't conclude that you proved that H naught was true, ever. We don't prove H naught is true because we already assumed it's true. Okay, this is a good place for a break. See you in a few minutes.